Good morning, everybody, and thank you for the invitation to speak at this year's IAH conference. Now, today I want to talk about a topic that's gaining greater focus within the group water scheme sector at present, and that is determining and indeed, where possible, implementing mitigation actions using the pollutant transfer continuum. Now, just to give a bit of a background on the group water scheme sector, over the past decade or so, the majority of regulated group water schemes have had preliminary source protection reports prepared, and depending on the abstraction type, a surface water catchment delineation or a groundwater zone of contribution has been defined for each of these schemes as part of that project. Now, if we look at the examples on screen, we will see that the catchment and ZOC types and sizes within the sector is quite variable. For example, the Kilmany-Ina Group Water Scheme in County Clare is an example of a small surface water catchment with limited inflow and located in an upland peat area, whilst the Glaslotte-Holland Group Water Scheme in County Monaghan offers sharp contrast in terms of both catchment size and pressures, being that there is both urban and rural pressures impacting upon Emmy Lough, which is the source of that particular group water scheme. Similarly, when we look at the groundwater zones of contribution, we will see that there is variability. For instance, the Listerline Group Water Scheme in County Kilkenny is an example of a small ZOC with moderate groundwater vulnerability, and in reality would only cover a number of fields, whereas the Greg Duff Group Water Scheme in County Meur is a much larger, much more complex ZOC given the karst nature of its environment. However, for the most part, when we're doing work in surface water catchments or groundwater ZOCs in relation to group water schemes, we do see, given the makeup of the group water sector, that they are dominated by agricultural lands. And I suppose it's for this reason last year that the Federation, with the help of many others, developed a handbook on source protection and mitigation actions for farming. Now, this handbook doesn't set out to reinvent the wheel, so to speak, but what it does do is it pulls together a number of measures that have previously been published by other organisations such as Teagasc and the Department of Agriculture, and indeed implemented in some cases in group water schemes. However, before we try and implement source protection actions, we need to know where the critical source areas are in the catchment. And just to define critical source areas, it's those areas that deliver a disproportionately larger quantity of pollutants or contaminants to the source once compared with other areas of the catchment. Now, and in order to do that and identify those critical source areas, in 2019, the Federation, again with the help with many other stakeholders, developed a framework for drinking water source protection. And that sets out a step-by-step process in how to try and identify those critical areas. As part of the Federation's framework, consideration is given to the pollutant transfer continuum, which is a landscape-based framework for considering diffuse contamination. Now, the plate or the flow chart on the left-hand side of the screen there shows the process the Federation is following when trying to decide upon appropriate mitigation actions. It highlights how they are considered according to the point on the source pathway receptor continuum on which they take effect. This allows for management strategies or mitigation actions designed to target relevant pollutants to be followed conceptually from application to impact, and provides clarity on what role a particular measure has. And the recommended relevant points along the continuum for consideration of specific measures include at source, so source reduction or source elimination, mobilization control, pathway interception, works at in-stream or at the receptor, and indeed treatment as the last step of the multi-barrier approach. And today I'm just going to give some examples of those. Now, while farmer engagement and collaboration may be required for actions at the various steps along the continuum, agricultural source reduction or elimination certainly is one of those actions that cannot be achieved without agreement or cooperation from the landowner. And where groundwater supplies have elevated concentrations of nitrate and have zones of contribution that are practically entirely dominated by agricultural activity, simply, in many cases, a nitrate reduction is the measure that's going to be most effective, or the measure that's going to be needed in those cases. In some of our group water scheme surface water bodies, sediment-based studies have shown that water quality deterioration began to heighten circa the 1950s and the 1960s, in line with a period of national agricultural intensification. However, and that's continued to decline to this day. However, in other situations, more recent agricultural intensification or diversification have caused water quality deteriorations. For example, a recent change in the landowner and therefore changes in the agricultural practices within the inner zone of protection in the Ballybricken group water scheme have seen nitrate concentrations become elevated. In fact, they're elevated above, for the first time in 2019, above the groundwater threshold value. And that was the first time that has happened since monitoring has commenced in that scheme in 2011. Now, through consultation with that new owner and with a bit of education on the landscape setting, a nitrate usage reduction was agreed in the inner zone, and that has seen the nitrate levels reduced to below the groundwater threshold value in the preceding year and indeed early into 2021. In other settings, measures aimed at breaking the pathway or a combination of a source reduction and pathway intervention may be required. And this was the case with Whitelock in County Monaghan, which is the source of the Sternuden Group Water Scheme, and was also one of the pilot sites for the Federation's Phase 2 Source Protection Project, which commenced in 2018. Now, on screen is a map of the Whitelock catchment, and Whitelock itself is positioned down in the southwestern corner of the catchment. And there are two principal sub-catchments that make up this overall catchment, and that being the Dromore River, which rises in the north and flows on down into Ballybay, into the Ballybay wetlands, and then on into Whitelock itself. And this is known as the Derry Valley subcatchment. And then we have the Loch Major stream, which rises over in the east and flows into and merges with the Dromore River just outside of Ballybay. Now, whilst both these subcatchments are relatively similar in terms of size, there is a sharp contrast again in terms of the phosphorus concentrations that are found in the water bodies in these subcatchments. For instance, this is an example of some of the phosphorus results that was taken in 2018. Now, annual averages subsequent to this have shown a similar trend, but in 2018, we can see at the monitoring point on the Dromore River, upstream of Ballybay, an annual average phosphorus concentration of 0.66 milligrams per litre was recorded, whilst in the Loch Major stream, an annual average of 0.028 milligrams per litre was recorded, which actually in itself would be classified as meeting the good water quality status. Now, when we look at the actual susceptibility maps for the catchment, it starts to begin to paint a picture and helps us conceptualize what actually is going on here. And we see in the Dromore River / Derry Valley subcatchment that it's dominated by lands that are classified as being highly susceptible to that near surface or overland flow pathway for phosphorus, whereas in the Loch Major stream catchment, there was a much higher proportion of free draining soils, which matches then with the results that we had seen in the water bodies itself. Also, when we look at the pollution impact potential maps for the catchment, we see, which accounts for stock densities, it adds stock densities to the equation. We see that there's quite a large amount of pollution impact potential maps ranking from 1 to 3, which is in the higher end of the scale. So it was thought that we know that we have a problem in the Derry Valley, so we needed to figure out what we could do in this situation. And when we done the calculation to see what sort of reduction was needed to bring that phosphorus level back down to in line with the surface water environmental quality standard, we calculated that an annual reduction of 550 kilos of phosphorus per annum would be required. So constantly it was determined that in order to meet this, we would need to implement a certain amount of pathway interception methods and mitigation actions. Here is a relatively novel example from the Sternuden project, whereby they're trying to implement a type of smart buffer approach. In this instance, extended buffers have been targeted and will be established at perceived runoff points, whilst the depths of that buffer then will be relaxed outside of these zones. Now, this approach as an alternative to a larger generic buffer width was met with greater approval from the landowner, who recognised the compromise that was needed in order to meet the water quality objective. There was also the perception, I suppose, amongst the farmer that there was less farmable land being lost. Now, it's understandable that in some instances, a dynamic buffer approach like that cannot be achieved, particularly where sheet flow conditions or there are multiple delivery points on a watercourse within a field or within one field. And that is the case, I suppose, in this example. This is an example of an extended buffer that's been established in the Grey Lone Loch catchment, which services the Moracloon Group water scheme in County Monaghan. And we see here that the extended buffer moves across the entirety of the field. However, if we were to look at this on a farm basis, there could be the potential elsewhere on the land holding that buffer depths could be reduced in order to compensate the loss of ground, whereas then this extended buffer is established at that critical source area. And perhaps even future agri-environmental schemes could allow flexibility in this type of approach in terms of reducing buffer depths in certain areas and then allowing for an extended buffer depth at critical source areas to ensure that they're being better mitigated against. The next generation critical source area maps produced and very recently released by the EPA are another valuable tool when trying to identify overland flow paths and delivery points within a catchment. Now on screen is an example of the high overland flow paths and delivery points within the Gartyloch catchment in County Cavan, which applies the Erne Valley Group water scheme. Now that particular group water scheme are in the process of developing an integrated source protection plan this year, and it's envisaged that these maps will come in very handy in helping to produce such a plan. Now it should be noted that groundproofing of these maps during winter conditions is likely to be required when designing field scale measures. And I just want to play a quick video showing what groundproofing of such maps might look like. Now, in this particular instance, a delivery point was located on the drainage channel feeding into the Dromore River, and a catchment walk was completed under and just after heavy rainfall conditions to verify the accuracy of this delivery point. And I suppose what could have happened here is that a buffer zone or extended buffers could have been implemented along the banks of the Dromore River itself, and that the drainage channel might have been omitted, which would have been an omission given the fact that that is where the delivery point is feeding into the system. So I suppose what this hammers home really is the principle of the right measure in the right place. Measures may also be targeted at the receptor, or in the context of this presentation, the drinking water source. Now, we know that wellhead protection is normally proposed or carried out to protect against more localized sources of contamination. However, in certain instances, proper wellhead protection can break that hydrological linkage between a wider catchment area. For example, the Templeport Group water scheme abstraction well is located within the floodplain of the Templeport Loch stream, and it has previously been known under heavy rainfall events to be inundated with floodwaters and has been marked by increases in turbidity concentrations. So really, I suppose in instances like this, without proper wellhead protection, it opens up the risk to a much wider range of potential contaminants that might be in the supply that would not otherwise be expected. In addition to meeting water quality objectives, consideration of the additional benefits from source protection actions for related environmental goals such as biodiversity, carbon sequestration, or indeed flood mitigation is recognised as being a means of achieving optimal outcome for the environment and even for public acceptance for the activity that you're looking to carry out. For example, sediment was also found to be a significant pressure within the Dromore River system due to livestock poaching and livestock access. And as a means of alleviating this issue, the scheme are proposing to carry out some riverbank rehabilitation works this year. Now, whilst obviously the principal outcome or the principal objective of the scheme is to see an improvement in water quality, it is thought that a reduction in anthropogenic sedimentation of the watercourse is likely to have a positive impact on a protected species, the white-clawed greyfish that do populate that particular river system. In addition, certain areas of the catchment native woodland will be established, and when those parcels of native woodland are established to intercept overland flow, that can truly be seen as an integrated approach, as it's going to give benefits to both water quality, biodiversity, and even some level of local carbon sequestration. It is imperative, however, that we don't become siloed in our thinking when designing such measures. Actions which have a positive impact on water quality need to be considered against any detrimental risk that they may have towards other aspects of the environment. Many group water scheme catchments or ZOCs are located within or partially overlap designated Natura 2000 sites. And whilst actions aimed at improving water quality from a drinking water perspective may have a co-benefit to designated sites with water-related conservation objectives, similar actions elsewhere may cause a disturbance. For example, fencing in the Glaslotte Holland group water scheme catchment in areas that overlap with the Slieve Bay special protection area would need to be alert to the fact that there is the potential for ground nesting birds such as the hen harrier in those areas, and that is indeed what the actual Slieve Bay SPA is designated for. So to conclude, as the protection of drinking water sources is now a cornerstone of the recently recast Drinking Water Directive, source protection is a very important role to play in the future of the group water scheme sector. And whilst mitigation actions aimed at reducing or eliminating contaminant load may be targeted at source, along the contaminant pathway, or at the receptor itself, we must ensure that the right measure is located in the right place in order to achieve the desired water quality outcome, as well as efficient and optimum use of resources. It's also very important that monitoring is undertaken at appropriate intervals to track progress and to determine if the implemented actions are effective or if catchment or ZOC activities are changing. And finally, source protection initiatives that incorporate additional or mutual benefits emphasize the connectiveness of nature and are therefore a means of delivering a genuine environmental and economic sustainability for communities. Thank you very much for listening.